All right. Today, we're jumping into one of the most powerful and, frankly, most important ideas in all of data science: maximum likelihood estimation. You'll hear it called MLE for short. Now, you might not have heard of it, but trust me, it's the secret engine running in the background of just about everything, from cutting edge research to the AI that powers your phone. Let's get into it. At its core, MLE is all about solving a problem that it feels like a detective story. You show up at a crime scene and it's surrounded by clues, right? That's your data. Your job is to figure out the single most plausible story, the one explanation that makes all of those clues just click. That's exactly what maximum likelihood estimation is designed to do. So let's start there. Section 1, the detective's question. We're going to frame the exact problem that MLE was built to solve. So here's the formal definition. MLE is a method for picking the parameters, think of these as the settings or dials, for a statistical model. And how does it pick them? This is the key. It chooses the values that make the data we've already observed the most probable thing that could have happened. It works backward from the evidence. And this right here, this is a really crucial shift in thinking. Normally, you might ask, what's the probability that my model is correct? But MLE completely flips that question on its head. It asks, given this particular model with these particular settings, how likely is the data that's sitting right in front of me? Then it just keeps tweaking those settings until that likelihood is as high as it can possibly get.
Okay, that might still feel a little bit abstract, I get it. So let's make it crystal clear with a super simple example. We're going to call it the coin toss test.
So picture this. Someone hands you a mystery coin. You have no idea if it's fair or not. You flip it 100 times, and here's your data: 65 heads, 35 tails. The parameter we're trying to figure out is the coin's true probability of landing heads. Now, your gut probably has an answer already, doesn't it? Well, MLE is how we formalize that gut feeling. First, we have to make an assumption. We assume the data follows a known pattern. For a simple yes-no outcome, like a coin flip, that's called a binomial distribution. No big deal. Step 2, we create a function, the likelihood function, that can calculate the probability of getting our exact result, 65 heads, for any possible level of the coin's fairness, which we'll call P. And finally, we just find the one value of P that makes our data, 65 heads, the most likely outcome of all. We maximize that function. And what value does it spit out? Well, you probably guessed it. It's 0.65. The parameter that makes 65 heads out of 100 tosses the most likely thing to happen is, of course, a probability of 0.65. And this is exactly why people love MLE. It just makes sense. It takes our common sense intuition. Hey, if I see something happen 65% of the time, the underlying probability is probably 65%. And it gives that intuition a completely solid mathematical foundation. But what is the math that's actually powering this common sense engine? Let's pop the hood and take a look in section 3, the likelihood engine. At the absolute heart of MLE is something called the likelihood function. You can think of it like a plausibility meter. You feed it a parameter, like a guess for our coin's fairness, say 0.5 for a fair coin, and the function spits out a score that tells you how plausible your actual data, the 65 heads, is given that guess. Our entire goal is to just turn the dials on our parameters until we get the highest possible score from that meter. Now, this slide is really important because it highlights that subtle but huge difference between probability and likelihood. With probability, we assume the model is fixed. We say, okay, given a fair coin, what are the chances of getting 10 heads in a row? We're asking about the data. But with likelihood, we flip it. We already have the data, 65 heads. And now we ask, how plausible is a model where the coin is fair? Or a model where it's biased? See the difference? We're judging the model itself. Oh, and a quick practical note here. When you're dealing with big data sets, the likelihood function often involves multiplying tons of tiny probabilities together. For computers, that can get really messy and lead to rounding errors. So in practice, we almost always use what's called the log likelihood. Taking the logarithm cleverly turns a giant multiplication problem into a much cleaner, simpler addition problem. It's a neat mathematical trick that just makes life easier for our computers. So, we know it's intuitive, we've seen the basic mechanics, but why is it a gold standard? Why do statisticians and data scientists absolutely love this thing? Well, that brings us to section 4. It turns out MLE has some really beautiful statistical properties. First, it's consistent. That means the more data you feed it, the more coin flips you do, the closer your estimate is guaranteed to get to the real, true answer. Second, with large samples, its behavior becomes predictable, kind of like a normal bell curve, which is fantastic for running statistical tests and calculating our confidence. And finally, it's efficient. It literally squeezes every last drop of useful information out of your data. Nothing is wasted.
Okay, so it's this powerful, classic statistical tool. You might think it's something from a dusty textbook. But here's the kicker. Its story doesn't end there. In section 5, let's see how this very old idea is at the very heart of the most advanced technology we have today.
Just take a look at this. Many of the most common machine learning models you hear about are, when you get right down to it, just MLE in disguise. When you train a linear regression model, its goal is to minimize the sum of squared errors. Well, it turns out that's mathematically the exact same thing as maximizing likelihood. Logistic regression, that's just a direct application of MLE. And even a giant neural network, when you train it for classification, its goal is often to minimize cross-entropy loss, which is just another fancy name for maximizing the log likelihood. Let that sink in for a second. Underneath all the complex jargon of training an AI or deep learning, a lot of the time what we're really doing is just a very sophisticated, high-tech search for the maximum likelihood estimate. We are simply asking the machine, hey, find the settings for your internal brain that best explain the data I've shown you.
So it's an incredibly powerful idea. It connects a simple coin toss all the way to complex neural networks. It seems almost perfect. But for this entire beautiful framework to work, there is one giant, almost philosophical assumption we have to make right at the very beginning. Any guesses what it is?
Here it is. We have to assume that our chosen model of the world, whether that's a simple coin flip model or a massive neural network, is the correct one to begin with. MLE is fantastic at finding the best fitting parameters for the model you've given it, but it can never ever tell you if you should have chosen a different model entirely. It's a powerful tool for sure, but like any tool, its ultimate value depends on the wisdom of the person who's wielding it.